Hi there, my name is Taylor Wiles and I am a kinesiology major with the hopes of going on to PT school. And for my current studies and my future career, biomechanics is a very important part of that, and it's also inextricably tied to physics and Newton's laws of motion. So biomechanics is the field of study that makes use of the laws of physics along with engineering concepts to describe the motion of body segments and also the internal and external forces which act upon them during activity. Now, to tie all that together, let's go over Newton's laws and some key examples of how they tie into biomechanics. So, lovely poster. Newton's first law is the law of inertia. This is basically an object in motion stays in motion. Now, this can be applied to biomechanics in a lot of different ways, but the example I'd like to use is with the gait cycle. So just a normal person walking down the street, their normal gait of the way they walk. Now during the swing phase of your gait, which is when you're taking the leg without the pressure on the earth, I guess, and you're swinging it forward to take your next step, it's in inertia, it has inertia. And in order to slow that down, you have to have the eccentric contraction of your hamstrings in order to stop that leg from just continuing on into space. Now this is both shows inertia and force is the contraction of your hamstrings. So that's a good biomechanical example of the first law. Now the second law is basically force equals mass times acceleration. Now this can be used in biomechanics in a lot of different ways, because with all human movements, this equation can be used to calculate the force. So muscles contract, obviously, when you're doing exercise to create a force, and that force is put onto body levers. Now to give a bit better idea of levers, I have a poster of the body levers, which in the body we have 3 body lever systems. So we have a first class lever, which is similar to having your head open and opening and closing your jaw. We have a second class lever, which really is only found in very few places in your body, and it's when you dorsiflex, so when you go onto your toes. That is an example of a first class lever. And third class lever is the most common lever in the body, and that's similar to like a bicep curl. Now, all of these different levers can also be described in different free body diagrams. So this is a free body diagram showing the muscles and kind of the whole body and where the force is, the effort, and the fulcrum. So this can be shown in a more simplified free body diagram as well, which kind of makes the concept a bit easier to digest. And it shows that basically these levers are all different based on where the fulcrum is, where the effort is, and where the load or the force. Load and force in this case can be the same. And also with these different levers you have mechanical advantage as well as mechanical disadvantage. So with a first class lever you actually have no advantage. With a second class lever, you have a mechanical advantage, and with the third class lever, you have a mechanical disadvantage, which is kind of funny that that's the most common lever in our body, but for our body systems, it works the best. So basically, this can be tied into the second law, force equals mass times acceleration, because when you contract your muscles, you create a force on those body levers. And so this is a very simplified example of this, but you can use this equation to basically calculate the force of any muscle on the body given a different activity or holding a weight. A very simple static example is just holding your head up, and the gravity and the mass of your head is countered by the muscles that contract in your neck and your lower back, such as the levator scapulae, your trapezius, and your posterior cervical muscles. So this is just kind of showing how body levers and the second law are tied together. Now the third law is the action-reaction law. So every action is met by an equal and opposite reaction, I guess, is a very simplified way to say it, or force. And in biomechanics, this can be used in many ways. A lot of times in, say, testing, when they're testing a runner's gait. So this is the example I have. Ground reaction force is a major thing that a lot of physical therapists and biomechanics kind of help runners study the way in which they step and how they could be more efficient in their steps. So if you are running on a force plate, you can diagram how the force, which is the force the runner is putting into the ground and the force that the ground is putting back into the runner, is measured on the force plate. So that is action-reaction. And from like this graph, you can see this is the force from somebody who runs with their rear foot as opposed to somebody who runs on their midfoot. And you can decide what is more efficient for different people. So the ground produces an equal and opposite force. And another example would be just like statically holding out your arm and holding a weight on your arm. And the opposing muscles are contracting with an equal and opposite force as long as your arm is staying steady. So if I had my arm just out like this and I had a weight in it and my arm was not moving, my muscles are contracting with an equal and opposite force to keep my arm level with the weight in it. If I were to move it, then that is different. Kind of goes more into the second law, Newton's law. But yeah, that is my interpretation of Newton's laws and how they tie into biomechanics. Thanks.